let's continue talking about the area under the curve. That's what we started talking about last time. Area under the curve. If you know something about doing this sort of problem, you can actually, this technique can be used in general to find the area of any kind of weird shape, as long as you are able to describe the equation that makes that shape. And what we're mostly going to focus on, for now at least, is shapes which are made in this way, where you have a function up here. This is the function f of x. And I want to find the area that it makes above some interval, and the area sort of under the curve, but above the x-axis. So that's the area that I'm referring to when I say the area under the curve. And for now, we are talking about estimating that area, but we are going to talk about how to get the true value of the area. But what we talked about last time was estimating this area by covering it with little itty-bitty rectangles. So the idea is, I'm going to redraw this just so that you can see. Let's say my function looks like this. I'm going to try and draw more or less the same thing again. From A to B, the idea to estimate that area is take the interval from A to B and chop it up into a bunch of little bitty bits. All right? And I didn't do this last time, but let's give the names to the bitties. So these like individual little points here, they're all x values, and the one furthest on the left is A, right? But I'm gonna call them like x1, x2, x3, etc. And A I'm gonna call x0. That's the sort of the 0th point. And then they go, you get a whole bunch of them. The last one I'm gonna call xn, which is also called B. But that's I'll call it xn. So n refers to we chop the interval into n bits, right? There's a total of n pieces. If you want to label the endpoints, you have to start from 0 going up to n, all right? The leftmost point is A going all the way to B. I was looking, I don't usually do this, but I was looking at the end of the notes that I wrote, from last class, just to see where I should pick up today. And I wrote this, I don't know if maybe you noticed this, I'm so embarrassed. I wrote this as the interval from A to B. I actually wrote the word B. I don't know what I was thinking. B is a number, not the word B. B. Very strange. All right, anyway, this is just how I'm going to label everything. And there are two strategies that you can use for how exactly you're going to draw these rectangles. And they are, you can draw the rectangles on the right endpoints or on the left endpoints. So maybe just to illustrate, I will draw the rectangles on the right endpoints. What that means is, it's probably going to be hard to even tell the difference over here, but towards the right you will see. I'm just going to sort of extend up each of these points into rectangles. Now, my picture is a little sloppy, but they should be evenly spaced points. And of course, the last one makes a rectangle. And since I said I'm using the right endpoints, I'm going to draw the rectangles so that they touch the curve on their right endpoints. So the height of each rectangle is determined by the point on the right side. This is just a choice. You could have also made it so that the heights are determined by the point on the left side, and that's called using the left endpoints. If you choose to do it one way or the other, you will get slightly different answers. All right? Anyway, what I just drew here, this is this is referred to as rectangles on the right endpoints. And then the sum of these areas, the sum of these rectangle areas is written as Rn, that big R for the right side. If I were to use the left endpoints, then you would call that Ln. So the n refers to how many pieces I cut it up into, and the big R means I'm using the points on the right side versus, I would say the left side would be written like Ln, right? Still, you can use those same points and just connect the rectangles up on the left side rather than on the right side. And that in our book is called Ln, all right? Let's try and do some examples. How would you actually add this up? This looks complicated maybe, but actually it's very simple to do. You'll have to like hit a bunch of buttons on your calculator, but from a theoretical point of view, it's very simple. Let's just try an example. You don't even need to look at the picture. I mean, I hope you understand what's going on in this picture, but when you're doing particular examples, it's actually not helpful at all to draw the picture. You don't even, I would say, don't even bother drawing the picture. Here's a specific example. Let's find R6 and L6 for this function, f of x equals x squared minus 2x on the interval 1 to 4. All right? So I'm not going to draw the picture, but what this represents is, that function. You could draw the graph of that function over this particular interval from 1 to 4, and it makes some kind of area, some kind of curvy area with the x-axis, and we are trying to estimate the area of that curvy shape. All right? So don't bother drawing the graph. It is helpful, in my opinion. If you've learned how to do this in high school, people have very different ways of writing the answers, and if you want to write it some way that's totally different from how I'm going to do it, that's totally fine. You can do it however you like. Here's how I'm going to write this. Let's just draw the interval. All right, I'm just going to draw sort of a little schematic here. It goes from 1 to 4. That's the part of the interval that I care about. And we want to divide it into 6 pieces. Now, hopefully, you can just sort of figure out by common sense where this will go. If I'm going to divide it in 6 pieces, maybe I'll cut it in half once, and then each of those 2 pieces cuts in thirds, right? These are meant to be evenly spaced. What exactly are those numbers on the bitty bits that I made, those extra endpoints here? I think if this is going to work out, that should be 2 and that should be 3, because I want to go from 1 to 4. And that means this first one is 1.5, then 2.5, then 3.5. All right? Like I said, hopefully by some kind of common sense, you can just figure out where those points are. If the common sense isn't happening for you, which, believe me, I've been there, we have this distance here, which is the same for every little bit, is called delta x. And actually, there's a cute little formula for delta x. So to find these points, if you can't just sort of by common sense figure out where they are, you should remember, this is important for other reasons, so you might as well remember this. There's a formula for delta x. It's b minus a over n. That's because b minus a is the total width of the whole thing, and I'm dividing that total width into n pieces. So the width of each little bit ought to be b minus a over n. And in this particular example, the b and the a are the 2 endpoints, right? In this particular example, it would be 4 minus 1 over 6, which is 3 over 6, which is 1/2. And that's how you would know, even if the common sense was failing you, that the width of this little thing should be 1/2. And so you would know that the next point should be 1.5. So if you can't work out the points just in your head, you can always calculate them in this way, b minus a over n. All right? Anyway, we have the points. Now, for the right-hand endpoints, so for R6, just so that I don't deface my chart from before, I will draw it again. I'm going to choose only the points on the right side of each of these intervals. So the points that I care about for the purposes of R6 are these ones. Those are the 6 points that will determine the heights of each rectangle. And I'm going to add together the areas of those rectangles. So we add up the base times the height each time, right? And the base is always delta x, which in this example is 1/2. The height is given by, sorry, I'm off the bottom. The height is different each time, but it's given by plugging that point into the function. And I'm going to for the R6, I'm going to use specifically those 6 points that I indicated right there. So the height is given by f of, can I just say like f of xi? What I mean by that is first you use f of x1, the first point, and then f of x2, and then x3, and so on until you get to the last point, right? And since I'm using the R6, I should start with this point, not the leftmost one, because when I'm using the right endpoints, we skip the very leftmost one and start with this one. Anyway, what's it going to be then? So, I did an example like this last time, so if you feel like I'm rushing here, it's because we already kind of talked about this. Anyway, I'm going to add together 6 things. Each time it will be the base times the height. So the first time it will be 1/2, that's the base, times, and then maybe I'll just say f of 1.5. I'll fill in the f's later. Then plus 1/2 times f of 2, 1/2 times f of 3, 1/2 times f of 3.5, and 1/2 f of 4, right? Those are the 6. Did I get 6 there? 1, 2, 3, 4, 5. What did I skip? I skipped 2.5. Sorry about that. Let me just squeeze them in right here in the middle. It's all right. I'm a professional mathematician. Okay. Now, if you were doing this on a quiz or something, this is more or less the answer. Although I would like to know that you know what the f represents. The f is supposed to mean the function that we're talking about in this particular example, which you can see. I haven't used it yet. It's right here, right? X squared minus 2x. So just so that everybody knows what we're talking about, on a quiz or something, I would expect you to actually plug in to the function x squared minus 2x. So it should be, when I do f of 1.5, it's 1.5 squared minus 2 times 1.5, right? And then I go 1/2, 2 squared minus 2 times 2, right? You just plug each of those values in. This is a real pain to write out by hand. It's totally fine with me if you want to do the dots. Now, if you're going to do the dots, you should give me a couple at the beginning and then also tell me where you end up, because this is the important difference between the L6 and the R6 is where you start versus where you end. So it's important. It's totally fine with me if you put the dots, but I want to know that you know where you should start and where you should end. So in this case, I go all the way up to 4 squared minus 2 times 4. And that's what R6 is, all right? If this was on a quiz or something, I would expect you to just leave it like that, and that's your answer. If you want to, for some reason, you could type all of this into your calculator, and you get, so I did this, I typed this into my calculator. I got 4.1875, all right? But if you don't care about calculating, typing that into your calculator is a real pain. But if you don't care about that, everything else is, I hope you agree, it's very, very easy. All you have to do is locate these points and then just write all this garbage, right? You don't really have to think much about anything. In particular, you don't ever have to do any derivative or antiderivative of anything. You just plug those values directly into the function as written. All right? So I hope you will agree. We'll do a few examples, but these are pretty easy. What about L6? I said do R6 and also L6. L6 is almost exactly the same. The only difference is, so for L6, that line is too big. The difference is which specific points to use. So again, we're going from 1 to 4, and I will just write these points again. This time I choose the left-hand points, which are these ones, right? And so for L6, it's the same sum that you can still see up here, only instead of starting at 1.5 and ending at 4, I'm going to start at 1 and end at 3.5. So I will say L6 is 1/2. I'll write it in 2 steps again. F of 1 plus 1/2 f of 1.5. Remember, these 1/2s are all delta x. That's why it's 1/2. In this example, 1/2 is the width of each little interval. And then all of this until we get to the final one, which in this case is 3.5. That's the last point we use for the left-hand rectangle sum. All right, and like I said, I don't want you to leave f's in your answer just so that I know that you know what you're talking about. You should plug in for the function like so. 1.5 squared plus 2 times 1.5, etc. The last one is 1/2 times 3.5 squared plus 2 times 3.5. All right, that's how we do it. This I also plugged into my calculator, and I got 1.9375. Now these two numbers, the R6 and the L6, are both, in general, you would expect them to be pretty close together because they are meant to be two different approximations of the same area, right? If you use a greater value of n, this 6, I divide it into 6 pieces. If you instead divide it into 10 or 100 pieces, these estimations would be much closer to the actual area, and you would expect them to be close to each other. Therefore, here they're pretty far apart. It's because in this particular example, like this last one, the difference between this one and this one is the inclusion of that last one or the inclusion of the first one. In this particular example, this is actually pretty big. Like this number, just this number by itself is that 4? It's 16 minus 8, which is 8, and then that 1/2 is 4. So the difference between the R and the L in this case, they're different by about 4. They're also different in the first in the first one. So in this particular example, these two things are fairly different, more so than I would generally expect them to be. All right. Anyway, this is mostly just sort of a bunch of mindless computing, and there's not a lot of real sort of work that you have to do. It's more an amount of just setting things in the proper spot and then writing the answers. All right? Any thoughts about that? What I would like to talk about probably will take up the rest of today is how could we find the area more accurately and eventually the true area, like with perfect accuracy. So for more accuracy, the basic idea is you increase the n. Increase the n, right? So instead of doing R6, go to R10 or R60. This will give you a more accurate measurement. The downside is the number crunching becomes much more complicated. In R6, you add together 6 things. In R10, you would have to add up 10 things. In R60, you would have to add up 60 things. For a computer, it's not a big deal, but if you're doing this by hand, you really don't want to do more than a few. But anyway, this is the idea. For more accuracy, you increase the n. And so, the true area will be this. Lim n goes to infinity of Rn, I will say, if the limit exists. So what our goal for the rest of today will be is to actually, can we somehow write this in terms of formulas, not plugging in individual numbers, but in terms of formulas, depending on n, and then eventually take that limit. That's what I would like to try to do. So this will involve doing something like this, but without choosing a specific value for n. Leave n as a variable the whole time, and then see if you can take the limit at the end. There are several sort of complications that arise when we try to do that, which is why it's going to take for the rest of our time today. But anyway, this is my goal. How could you actually set up that limit in terms of n, and at the end actually do the limit, take the limit as n goes to infinity? All right. Let's set it up more abstractly. So this is why I said we were going to write these points as like x1, x2, x3 up to xn. This is the very basic first step in keeping the n as a variable. Our interval will look like this. We begin with x0, then x1, then x2, etc., all the way up to xn. Sometimes it's helpful to write the second to last point, although it's not really going to be a big deal this time. But can anyone say, how would you write this? How would you indicate the second to last point? The last one is xn, yeah? Yeah, it's x and then a little n minus 1 like that. This is if the n is 100, that would be x99. It's just one less than the last one. Yeah. Okay, these are the individual points. So if you're writing it this way, then Rn we could write as, remember what it is. You add together a bunch of stuff, and each time it's going to be delta x times f of whatever point you're plugging in. So it'll look like the first one will be delta x times f of x1, followed by delta x times f of x2. Because Rn uses the points on the right side, right? These ones, all the way up to the very last one. Skip over the leftmost point. And then finally, finishing up, obviously I am going to use the dots here, f of xn, like that. Right? So you start with x1, then x2, all the way up to xn. This we are typically going to write using the summation sign, which I hope that you are familiar with. So rather than writing a bunch of pluses with the dot, 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 this we're going to use the sigma notation for this thing. And I'm going to use a little I for the sort of the counter variable in the sigma. So this would look like the sum I equals 1 to n of delta x times f of xi. So I hope you're familiar with this sigma notation. It means this big thing here means you're going to add up a whole lot of stuff. And what is the stuff you're adding up? It's this. And you start by using I equals 1. You add that. Then you increase the I. You go to I equals 2. You add that. You go to I equals 3. You add that. And keep on adding until you reach this number at the top, the end here. That's where you stop adding. So that's this here. Now, in our book, actually, they always write this formula the other way around. So it's always written this way. Rn is the sum I equals 1 to n, f of xi, delta x. I've been writing the delta x first just because I like to say base times height. Delta x is the base of the rectangle. But, of course, it's the same as this. That's a multiplication, so you can move it around to the other side. That's what Rn is as a formula, leaving n as a variable. You could also do Ln is very similar. The only difference is Ln should start with x0 and only go up to this second to last one, xn minus 1. So the corresponding formula for Ln is this. The sum I equals 0 to n minus 1, f of xi delta x. All right, that's the formula for Ln in general. I suppose you could memorize those formulas, but actually I wouldn't really suggest it. If someone asked me to find like R5 for some particular example, I would not plug 5 for n into this formula. I would just draw the interval and work it out. Although you do you, however you like. All right. So what I want to do is try to do a specific example in which we do those sums and then actually take the limit as n goes to infinity. That's what I said our goal for today would be. There's actually a name for that. We get the true area when we take the limit as n goes to infinity. I said that before. The true area by doing lim n goes to infinity of Rn. Or actually, you'll get the same answer if you use the Ln, because either strategy, using the right endpoints or the left endpoints, ought to give you the true area if you increase the n high enough. So we get the true area by doing those things. This is called the definite integral. And it's written using the integral sign. So I'm going to write this like a official definition here. So this is called the definite integral. There's also something called the indefinite integral. So that's why this is called the definite integral. There's another thing called the indefinite integral. But anyway, the definite integral of f of x on the interval a to b is written like this. There's a special notation for the definite integral. It has this cute little thing called the integral sign. It's written like that. The integral, and when I see that, the way I say it, I say the integral from a to b of f of x dx. All right? This a and the b, the integral sign was, I believe, invented by Euler, the mathematician Euler, and it's meant to look like the letter S because it is meant to somehow be analogous to the sigma. You think of this integral in the context of the definite integral. The integral is kind of like adding together a bunch of stuff. It's just that what you're adding together are tiny, bitty rectangles, right? Really, sort of informally speaking, you're adding together infinitely many rectangles of infinitely small widths. Although that doesn't really make sense exactly what I just said, but that's what this is meant to represent. Then you have f of x, which is the function which determines the heights of those itty bitty rectangles. And then you have this dx. This dx doesn't actually really mean anything by itself. It just indicates that that first of all, it tells us that the variable in this integral is x. And it also is meant to be kind of reminiscent of this delta x here. This is supposed to, the way we write this, is supposed to resemble this sum. So the sigma instead becomes this weird elongated s, and the delta x instead becomes this dx. All right. It's a kind of a strange notation, but it looks cool to write an integral sign. You can impress your friends and loved ones with your fancy integral sign here. Anyway, what the definition is, I didn't say this is not a definition yet. I just wrote how you write it. The definition is, this is written like this, and it's defined as the integral from a to b, f of x dx, is equal to this limit. The lim n goes to infinity. The sum I equals 1 to n f of xi times delta x, where I have to tell you what those things are. Delta x is equal to b minus a over n, and xi are the endpoints of the intervals. When we divide the interval a to b into n pieces, and equally shaped or equally sized pieces. All right. This is all mostly terminology, but that's the definition of the definite integral. And what it represents the actual area under the curve of the curving shape that the function makes. All right. I just want to say one more bit of terminology. This sum here, which is what I was talking about before, this is called a Riemann sum. Riemann is the name of a German mathematician who was one of the, these ideas had been around before Riemann, but he was one of the people who really formalized this notion of doing the definite integral by adding up bitty rectangles. All right, a Riemann sum. Don't say Riemann or Riemann. You sound foolish. It's Riemann. There's a major, one of the biggest unsolved problems in mathematics today is called the Riemann hypothesis. Check it out. You win $1 million if you can figure it out. It's an unsolved problem that Riemann first suggested, like in the 1800s. It vaguely has to do with the distribution of prime numbers, but yeah, that's a big deal. All right, let's see if we can actually do this. So I would like to, I'll say in simple examples and some complicated examples, we can actually compute this limit. Let me tell you, just so that we're honest with one another, when you do integrals, usually in a class like this, we are usually not going to do it by finding the limit of the Riemann sum, because this is quite difficult, as you're about to see. Just like doing the derivative, you sort of first learn how to do the integral using the definition of the Riemann sum. But after a while, you can begin to deduce some patterns and learn some tricks. And so, like in your real life, beyond this course, usually when you're trying to do an integral, you will use some kind of awesome tricks that you just have memorized, just like for the derivative. You don't typically use the definition of the derivative to find the derivative of something. You memorize sort of a short list of tricks which can generally apply to anything that you might encounter. And the same is true of the integral. So we're not usually going to do the integral sort of the hard way. That's what we're about to do. We're going to learn some tricks soon enough that makes it so that we don't have to do the limit. But for now, let's try to do some simple examples using the limit of the Riemann sum. So let's do this integral. Integral from 0 to 1, x squared dx. Let me just try and draw what this represents as an area. It means the area under the curve of this parabola, x squared, right? Like this. This is the x squared parabola. But only the area on the interval from 0 to 1. So that's like, here's 0 to 1. Goes up to here. Now the y value at 1 is also 1 because this is x squared. So the y value would be 1 squared there, which is also 1. So what I'm talking about is this area right here. All right. This is the kind of area that no kid learns the formula for the area of a weird sort of triangular shape with a parabola on the top. But, it does have some area. I don't know if you've ever seen this before. My mind was kind of blown the first time I saw somebody do this example, because when I see that weird shape, I expect the answer, the area, to be just some weird number, right? Maybe involving a square root of something or something. It turns out actually this area, there's no reason for you to believe me, but it's a fact. This area is 1/3, which is, I don't know if that seems interesting to you. That was very surprising to me. I can still remember, as a young lad, new to the ways of the world, when I learned that the area under the parabola right there is 1/3. I was shocked by this fact. Why should it be such a nice, cute little number there? Does it mean that if you took 3 of those things, you could add them up into a perfect square? Well, yes, but it's not at all obvious how you would do that, because it's not, it doesn't look like 1/3 of a square to me. It's a weird shape. It's just one of those things. Sometimes, the world is more interesting than we thought it was going to be. Anyway, let's see if we can do this. So, just very naively starting off, it's this, right? This is the definition. It is the lim n goes to infinity of Rn, right? And what is Rn? I'll write that definition also. It's the sum I equals 1 to n of f of xi times delta x. And let's see if we can actually plug some of this stuff in. You have to do it leaving n as a variable at all times. Now, it's not so hard to plug in for delta x, right? Because I said before, there's a cute formula for delta x, which you should memorize eventually. It's b minus a over n. And in this particular example, the b and the a are 0 and 1, so this is going to be easy enough. It's going to be 1 minus 0 over n, which is just 1 over n, all right? So that I'm going to plug in for delta x is 1 over n. That's not so bad. What about the x with a little I, all right? That means we have to predict exactly where each of those little bitty points is going to be when you divide the interval up into a bunch of little bits. Here's the trick for that. Xi, it always is, you can find that point by adding together a bunch of delta x's. And when I write this down, I hope it will seem clear. This is another formula, I suppose, that you should memorize, although it's very commonsensical. To get point number I, you start with the leftmost point, which is x0, and then you just move over by I bits, or I chunks, right? That's why it says x0 plus I times delta x. x0 is the leftmost point, and then you add on the small widths, I of them, all right? So, in our particular case, what is this going to be? x0 is the leftmost endpoint, which is 0. So this is going to be, so in our example, xi is 0 plus I. I leave I as a variable because it's going to appear in the sum here. Delta x, I have already determined, is 1 over n in this example. So just writing that in a nicer way, xi is I over n, isn't it? Yes, it is. All right. So we can plug in. I have determined a formula for delta x is 1 over n, and a formula for xi is I over n. So this says, just stretch it out a little. Sorry. The sum I equals 1 to n. F of xi is f of I over n times delta x is 1 over n. All right. Can we continue to simplify? What can you do with the f? Any ideas? What can we do something with f of I over n? I think we know what the function f is. What is it? It's the squaring, right? I said at the very beginning, we haven't used this yet, but the whole point of this was right here. I'm trying to find the area under this curve, x squared. So the f here means squared. So when it says f of I over n, that means I over n squared. I equals 1 to n. This is I over n squared, and then times 1 over n. All right. Can we simplify this? Well, you can do some simple, algebra here. When you have the fraction squared, that means you square the top and also square the bottom. I hope you remember how to do them fractions. So I can write that as, this is I squared, isn't it I squared over n cubed? I have two n's in the bottom from the square thing, and then another 1 over n over there. I just put them all together. All right. And I might as well tell you now, there are some nice tricks you can do with summations, which hopefully you've seen these before, but in a sum, we can factor any constant out. And by constant, I mean no i's. So in this example, actually, we can factor this n out of the summation. And I mean, it looks like a variable. It kind of is a variable, but it's a constant as far as this sum goes, because what this means is you add together a bunch of stuff, and those stuffs, they all have the same n cubed in them. And so this thing can come out to the front. Not past the limb, but it can come out to here. And then it's like that. Right. I factored out the 1 over n cubed, leaving on the inside just x squared. And now we're kind of getting there, but actually this is a bit of a dead end, or a roadblock at least. How do we do this? Come on. This. Huh? It turns out there are special tricks for finding those kinds of sums. And this is something we need to take like a 15-minute detour to talk about. How do you find those kinds of sums? So we'll come back and finish this example. We're almost done, if not for this special trick to find that sum. So I want to talk about tricks for sums. And in particular, what we're going to talk about is sums like this. I equals 1 to n of I, or the sum I equal 1 to n of I squared, or the sum I equal 1 to n of I cubed. There are formulas for these, and we're only going to go up to I cubed. There are more formulas for those if you want, but we'll just go up to I cubed. And then actually, we're also going to do like I to the 0, which would just be 1. This is the easiest of them all. All right. So within 10 minutes, we will know formulas for these forms of sums that you should memorize maybe the first one, but I will give you a list of these on our next test if you have to use them. You should expect to have to use them. All right, let's talk about the easiest one is the last one. Easy would be sum I equals 1 to n of 1. Think about what that means. It means you're adding together over and over again, and the thing you're adding is just 1 every time. So what this means is 1 plus 1 plus 1, etc., ending up with 1, and you're adding this up n times. Any geniuses of addition out there? What does it add up to? So want to shout it out? N. I hope you are all shouting it out in your heart. N. If you add 1 together over and over again, n times, it adds up to n. Yes, n is correct. Okay, that was the easy one. The other ones are a little harder. How about medium is the next one. I equals 1 to n of I, all right? What this looks like is you keep on adding up the stuff. The first time through, you start with I equal 1, so you get 1. The next time through, you start with, you use I equal 2, and then I equals 3, and then 4, and so on, all right? This is the sum of I. It would look like that if you were to write it all out. Now, what does this add up to? This is much less obvious what it all adds up to. But it turns out there's a cute little trickety trick about figuring out what this adds up to. So the cute trick is, well, let me tell you, actually, this formula right here is the subject of a sort of a mathematical legend that everybody talks about, although there's no real evidence that this is actually true. But this is a story about the mathematician named Gauss, who is regarded now as one of the all-time greats. He was like late 1800s, I believe. And apparently Gauss was a little kid, and he was at school, and his teacher was really annoyed with the kids and just wanted to have a smoke break or something, and said, all right, kids, leave me alone for a while. I would like you to add together all the numbers from 1 up to 100, expecting the kids to spend the next 10 minutes just doing these, adding over and over again. And the legend says that the child, Carl Gauss, immediately shouted out the answer, ruining the teacher's plan for having a smoke break or whatever the teacher wanted to do. Because the child, Gauss, was so smart that he came up with this cute trick on the spur of the moment. The trick is to add together the first ones and the last ones. You group together the things on the beginnings and the ends. Check it out. If I were doing, say 1 to 50, you write it out, but you kind of balance it out at the end also. So 48, 49, 50, those are the last ones. And what I said is you sort of group them front to back somehow. So I'm going to think of this one goes with this one. This one goes with this one. This one goes with this one, right? And you add them up in this way. This is the cute trick that Gauss allegedly came up with all on his own. This trick has been known, many centuries before. The child Gauss. This is a made-up story. How the trick works, though, is if you think of them as grouped this way, each group adds to 51 in this case, right? The 1 in the 50, the 2 in the 49. That's the point of doing this cute trick, is that they all add to the same amount, 51, which in the general case, this is n plus 1, right? If I'm thinking of the n as being 50, each of these pairings adds up to n plus 1. And how many of these pairings are there? I'll say the number of groups How many are there? Like in this case of with 50, how many groupings are there? Can I hear from somebody else? He answered the easier questions. 25, yeah. Since you paired them up, there were 50 total. You group into pairs. There's going to be 25 pairs. So the number of groups is 25. This is n divided by 2. All right. And so that means the total sum is n plus 1 times n divided by 2. You have that many groups. Each one adds up to 51. So the sum is n over 2 times n plus 1. This is typically written this way, n times n plus 1 over 2. All right? This number actually is useful in many different situations. These sums, they come up in some kind of simple geometry problems. For instance, the number of, anybody into bowling? This is a standard setup of bowling pins. There are 10 pins in the standard bowling setup. That's because 10 you can think of as 1 plus 2 plus 3 plus 4. These are the four rows of the bowling pins, right? It adds up to 10. If you wanted to put another row on there, you could do bowling with 15 pins if you want, or bowling with 21 pins, because that's the next, if you put on the next row. Those are referred to as triangular numbers because you can make these sort of triangular arrangements of points with them. I remember when I first played the Wii bowling. Remember the Wii bowling? There was, in the original version, there was a mode you could turn on, 100-pin mode, which my kids loved, where they set up 100 pins. And I was always vaguely unsatisfied with that. Immediately when I saw that, it's because because of my mental condition, I immediately thought 100-pin bowling is ridiculous because 100 is not a triangular number. Actually, if you tried to you can't make a triangle out of 100 pins. There's like a few that are missing on the ends, which always dissatisfied me. You need like go to 104 pins or something, but they didn't want to do that for the Wii bowling. Anyway, this is the formula for triangular numbers. One of my mathematical friends was actually retweeted by the Solo company. You know they make the red beer cups, the Solo cups. They sent out a tweet once. They had a picture of cups, like stacked in a pyramid. You know, that's how people always stack the cups. And they said, somebody was like at the store or something. They tweeted at the Solo company, I need to make a stack of cups that has 10 cups across the bottom. How many cups total do I need to buy to make that happen? And my buddy immediately tweeted back, this formula with 10 plugged in for n. That's the answer to that question, because it has to do with these triangles. All right, anyway, there's a bunch of random facts about this formula. It comes up, it's a useful formula in many different scenarios. And he got retweeted by the Solo corporate account, which he thought was really awesome. So just to summarize, the sum of 1, I equals 1 to n, this is n, and the sum of I equals 1 to n, is n times n plus 1 over 2. Those two you should remember. I'm just going to tell you the other two, which are more complicated. We're going to use them in examples, but I won't expect you to memorize the other two. The other two are this. The sum of I squared, I equals 1 to n. This you can compute by doing something like this triangular reasoning, but it's like in 3 dimensions. You can do some tricks to figure out, here's the formula. I will just tell you. It's this. Why exactly is it that? I don't want to get into it. They actually explain this in the book, in the appendix, if you're interested in where that formula comes from. I don't want to get into it. That's the formula of the sum of the first n squares. So this would be 1 plus 2 squared plus 3 squared plus 4 squared, etc. You get that. And the sum of cubes, again, I don't want to talk about where this formula comes from. It's this, n, sorry. It's actually, this one is not so hard to remember because it happens to be the same as the triangular number one, but squared. All right, that's the sum of I to the third. So put this in a box somewhere. You will want to refer to these when you are finding the limit of the Riemann sums. And like I said, I will expect you to know the first two without looking them up. The second two, I will, if you want to do this on the test, I'll give you the formula. All right? So can we revisit that example that we were doing before? So to finish the example, integral from 0 to 1 x squared dx. All right, where we left off was, it was lim n goes to infinity of, after we plugged everything in, we were looking at this, right? I believe that's where we ended up with that example before. And now that we know the formula's in the box, we can plug in for that sum. This sum, I equals 1 to n of I squared, is that. And then we'll just be able to find the limit. So we get lim n goes to infinity, 1 over n cubed times this big formula, n plus 1, 2n plus 1 over 6. And now we're just about done with this example, right? There's no more sum in there, so now it's just a matter of finding that limit. And you do this using the old tricks that we talked about a few weeks ago about finding limit as something or other goes to infinity, right? For things that look like this, and actually in all of the examples from this section, it's just a matter of the old trick where you divide out by the biggest power of n that you can see, right? Usually we do this with x, but in these problems it's always going to be n. So maybe I will just rewrite this first of all as, okay, on the bottom it's, oh, sorry, get out of here. On the bottom it's 6n cubed, and on the top it's this stuff, n plus 1, 2n plus 1, right? And I'm going to divide the top and the bottom out by the highest power of n, which is going to be n cubed. Now, on the top, it's a bit of a pain. You see those binomial things, which if you really wanted to work out what the top is, you'd have to do the FOIL up there and a bunch of distributing. Would you mind? This is, in practice, never really necessary. I'm just going to say the first part of it is going to say 2n cubed. That's because the highest degree term comes from taking this n, and this 2n, and multiplying them all together. Now, when you do all the foiling, distributing, there's going to be a bunch of other stuff here, but it's all of lesser degree than 3. And so it's not going to matter when I divide out everything by n cubed, right? All those other things are just going to go away when we divide everything out by n cubed. So the answer for the limit will end up being 2 over 6, all right? When you divide through everything by n, sorry, I didn't mean to, I just did the limit. I shouldn't have written lim there. That is the limit, right? You're going to divide everything on top and the bottom by n cubed. Everything in the dots up top will cancel, and everything else just gives you, 2 on the top and 6 on the bottom. That's 1/3. That's what I said it was at the beginning. All right? Now you have a reason to believe me that I said that area really is 1/3. All right? That one example took quite some time. I want to just do one more, and I think that'll do it for today. All right? Let's try one more. I'm going to do the same function, x squared again, but using a different interval. So let's try interval 3 to 5, x squared dx. Same function, different interval. All right? I'm going to try and summarize kind of how we started off, because maybe I never put these two formulas in a box. These are super important. When you're doing the Riemann sums, you always are going to have to do this. All right. Those you definitely need to have those as part of your sort of bag of tricks. Actually, instead of x0, maybe I'll write a. It's the same. But since I used a's and b's in the first formula there, I'll use a in the second one. All right. every time you do one of these Riemann sums, you have to use those two formulas to get yourself going. It's a matter of setting it up. I mean, it's in theory kind of like doing the definition of the derivative. You set it up, you do a whole lot of complicated simplifying, hopefully not screwing it up, and at the very end you take the limit. It's the same with this. Let's just see if we can do it. You just got to keep it all straight. So it's integral 3 to 5, x squared dx is the limit, n goes to infinity, of the sum. This is where you always begin. 1 to n, f of xi times delta x. All right? And from here, we just plug everything in, do a bunch of crazy simplifying, and eventually take the limit at the very end. And don't screw it up. There's lots of chances to screw it up, unfortunately. Maybe on the side I'll work out, in this particular example, what is delta x and what is xi? Delta x is b minus a over n. That would be 5 minus 3 over n. And you leave the n as a variable, because I'm eventually going to take the limit as n goes to infinity. Don't try to plug something in for n. So anyway, this is 2 over n, right? That's the delta x in my example. And then the xi, a plus I delta x. A is the lower of the endpoints, which is 3. So it's 3 plus I delta x. I is just I. Delta x is 2 over n. So it's 3 plus I times 2 over n. You are never going to plug something in for I or n. They have to always remain variables, because I is the summation variable and n is the limit variable. This, maybe it'll be a little simpler if I write 3 plus 2i over n. Just put those guys together. It's a good idea to sort of simplify as you go, because it's only going to get more complicated when we start plugging it all in. All right, let's do it. So down here, I'm going to say f of xi is f of 3 plus 2i over n. And then delta x is 2 over n. I hope I did it right so far. Plugging in the delta x and the xi. All right. Now we got to do the f. In this example, f is still x squared. So I'm going to do the f. I got sum I equals 1 to n out here. F of 3 plus 2i over n means that thing, 3 plus 2i over n squared. And then times 2 over n. The f in this example is x squared. It's not always x squared, but it's just because in this case, the function I'm taking the integral of is x squared. So that's what we do. All right, let's see if we can add it or simplify here. What I got to do next is actually do the FOIL here. This is a bit of a pain, but I need to square that out. So it's going to be, you can do a little business on the side if you want. 3 plus 2i over n times 3 plus 2i over n, right? Do the FOIL with that. What you get first is the 3 times the 3, which is 9. I like that. Plus, in the middle, I get 2i over n times 3. And on the outside, I also get 2i over n times 3. That's 6i over n each time, and I get 2 of them, so that's 12i over n. I think I did that right. You get 6i over n 2 times, so you get 12i over n. And then the ones on the end, 2i over n times 2i over n, which would be, if I multiply it out, 4i squared over n squared. That's 2i over n times 2i over n. All of that is still in parentheses times 2 over n. All right? This is now as complicated as it's going to get. From now on, we are just going to simplify it down. And eventually, take the limit as n goes to infinity. Let's see. Sum I equal 1 to n. We got to distribute the 2 over n across the sum there. All right. So 9 times 2 over n, I will write as 18 over n, plus 12i over n times 2 over n, that's 24i over n, plus 4i squared over n squared times 2 over n gives me 8i squared over n cubed. Sorry, the one in the middle has that n squared on the bottom. I think those are right. All right. This particular example requires one other trick that we didn't have to do in the previous one, and that is you can break up the summation. If you have a sum inside the sum, you can break it up into several sums. Break up the sum. What I mean by that is you just add I equals 1 to n of 18 over n plus the sum I equals 1 to n of 24i over n squared, and then plus the sum I equals 1 to n 8i squared over n cubed. All right. This is another rule about summations. You can break them up like that. Because why is that valid? I mean, here it means add this together over and over again, these three things. That's the same as if you added up the first thing over and over, and then the second thing over and over, and then the third thing over and over. You get the same answer. All right, how are we doing? We're almost done with this, maybe. The sort of next to last step here is let's factor out all the constants that you can from each of these sums. The first sum is actually all constants. This we can pull out everything, 18 over n, and then it's just the sum of 1 would be left over after I factor that out. The next one, we have to leave the I on the inside, but you can pull everything else out. 24 over n squared pulls out. And then what remains is the sum of I equals 1 to n. And then the last one, you got to leave I squared inside, but everything else can come out. 8 over n cubed, the sum of I squared. And then we're going to use them formulas in the list, right? Each term there has the sum of something or other. The sum of 1, remember, is n. That was our very first easy formula. 18 over n. The sum of 1 is n. Next, I got 24 over n squared in the front. And then the sum of I, that's the Gauss's trick, n times n plus 1 over 2. And then the last one, 8 over n cubed out front. And then the sum of I squared, that's the first of the non-easy ones. It's this, though. I happen to remember. All right. And now, finally, we're going to do the limit. Something seems weird about this. Sorry. No, that's all right. I thought I messed it up. How do we take the limit as n goes to infinity? Really, I have sort of three pieces. I'm going to think of them separately. Can we just maybe simplify a little bit? The first piece, 18 over n times n, is just 18, right? So when I take the limit, that 18 is just going to stay like an 18. The next one, 24, I have a 24 on top and a 2 on the bottom. That could simplify to a 12. And then what's left is n plus 1 over n squared. And then the last one, I have an 8 on top and a 6 on the bottom. Well, maybe I'll just leave the 8 out front and write this. 2n plus 1 over 6, all right? And we can take the limit in each part. The 18 stays like an 18 because there were no n's there. This gives me 12 times, what's the limit of this part? Again, you want to think about the coefficients on the highest term on the top and the bottom. On the bottom, the coefficient is 1. And on the top, I think it's going to be 1, right? It's going to be n squared plus 1. So that limit is 1 over 1. And then I have 8. And again, think about the coefficients on the top and the bottom. This is like the previous example. It's going to be a 2 over a 6. Yes?
Where did the n cubed in the denominator of 8 over n cubed go?
Oh, it disappeared. It should. Thank you. It should be here. Yeah. Actually, you need it to be there in order for this, what I just said, to be true. I have n cubed on the bottom. It's also going to be an n cubed on the top. The n cubed on the top will have a 2 in front of it. On the bottom it has a 6 in front of it, and so the answer that you get will be 2 over 6. All right, that's the answer. These numbers, you can add them up if you want. This 18 plus 12 is 30, and then plus 8 thirds. That's the answer. A lot of work for it. You get a number at the end, which is this number represents the area under the parabola from 3 to 5 is that number exactly. All right? These are difficult. I mean, this will take you a while, and there are many, many chances to mess it up. So next time, sorry, this whole class has been just me talking. Next time, I'm going to have some examples for you all to try, and we'll have a grand old time together. All right?